Howdy, howdy. This is Mr. Potter. In our previous lessons, we've been talking about how to undo the chain rule, because the chain rule is the derivative rule that kind of gives us extra terms, or we end up with the product of two terms, the function itself, and then the derivative of the innermost of our composition of functions. But what we're going to do today is we're going to talk about another of our derivative rules, namely the product rule. So I want to real quick just do a real quick recap of that. The idea is that we're going to be starting off with some product of two functions, and if we're taking the derivative of a product, we end up with the first function times the derivative of the second, plus the second function times the derivative of the first. So this was the product rule as we learned it back in chapter 3. But one of the things that we've been talking about are the concept of antiderivatives, the idea that I can work backwards from a derivative. So if I have the antiderivative of f times g prime dx, this should be equal to the antiderivative of this first term plus the antiderivative of this second term. And the idea behind this is twofold. One, the idea that if I'm taking the antiderivative of a derivative, these are inverse operations, so they're going to undo each other. So I really have just f times g, just plain functions. But this is going to be equal to the sum of two indefinite integrals, f of g, f times g prime, and g times f prime. But the other idea here is that I can actually solve for one of these terms. I can actually say that the integral of f times g prime dx is equal to f times g minus the integral of g times f prime dx by moving this term here to the other side of the equation. So I can solve for one integral in terms of a product of two functions and another integral. And the reason that I would do that is the idea that I would start off with something that seemed pretty hard, and this resulting integral should be easier. And so that's really the scope that we're going to be taking a look at. This integration by parts that we're going to be talking about is if I can find some way to decompose a product of two functions into a function itself and the derivative of some other function that's fairly easy, then I should be able to write it as f times g minus another integral, and I'm hoping that this integral will be easier. Just keep in mind that what we want is we want f to simplify when we take derivatives. And I want g prime to be easy to find the antiderivative. So that's really the idea here. I'm going to have to choose my f and my g prime judiciously, and we'll talk at the end of this video about a quick way that we can do that by inspection. But I want to talk about a few sample functions. So let's go ahead and take a look at this first one. I've got the integral of x times ln x dx. Now remember what I said is that f should simplify when I take the derivative, and this g prime should be easy to integrate. So looking at these, one of these looks pretty hard to integrate. I know that I can integrate x because the power rule would give me x squared over 2. But we haven't actually learned a way to integrate natural log of x. So really only x would satisfy this idea. And so f is something that would simplify, and I agree that a logarithm transforming into a rational function, 1 over x, when I take the derivative, is a simplification. It's not a grand simplification, but it does simplify. I mean, we learned about reciprocal functions back in Algebra 1, but natural log was something we introduced in Algebra 2 and really took off in our pre-calculus class. So the idea is that if I have that f is something that simplifies, it's natural log of x, and dg, this is really dg dx, which is going to be the x dx that I've got here. So I've actually got g prime. Then I can find df, because df should be the derivative of natural log x, which is 1 over x dx. And I said that dg should be something that's easy to find the antiderivative of. That's going to be our x squared over 2 plus a constant. Now, I'm not going to worry about this plus a constant until the end, after I'm done with all of my antiderivatives. So right now I'm just looking at the functional aspect of it. But we said that the integral of f times dg we said that the integral of f times dg would be equal to f times g minus the integral of g times df. And of course, the idea was that I would start off with something that was hard, and I'm really hoping that what I get is something that's easier. And this certainly looks like it's going to be easier. So, as a matter of fact, it looks like it's just going to be polynomial in x. So what I've got here is x squared over 2 times the natural log of x minus, this is the integral of x over 2 dx. And in reality, I could write this with a 1/2 in front and only look at the x and take the antiderivative of this. So we end up with x squared over 2 times the natural log of x minus 1/2 times the antiderivative of x, which would be x squared over 2 plus a constant. And this is where I said I would take care of the constant after I've taken care of all of my antiderivatives. The idea of integration gives me a constant every time I integrate. But since we're adding and subtracting, I can combine these into one grand constant. Now, if I want to rewrite this, I notice that I have an x squared over 2 as a common factor, and this is really the natural log of x minus 1/2 plus a constant. So what we're doing here is we're rewriting our integral from something that's hard to something that's a lot easier to work with. That's the power of this integration by parts technique. But it all is essential that we take a look at these ideas for finding f and g prime. F should simplify when I take a derivative, and g prime should be easy to integrate. If I had chosen poorly, if I had chosen that I wanted f to be equal to x, because the derivative of x certainly does simplify, I would end up with dg being the natural log of x dx. And I don't have a way of finding out what g is because we haven't talked about finding an antiderivative for a natural log. We will near the end of this video. As we were talking with u substitution, practice really is the key here. The idea is that the more I practice, the more I expose myself to situations where I have to use this technique, the more comfortable I'm going to be with this technique. So I've got another example here. I've got the integral of x times cosine x dx. And again, remember, I'm looking for an f that simplifies when I take the derivative, and a dg that's easy to integrate. So looking at these two terms, I've got an x term and a cosine of x term. One of these has got to be f. And both of these I can take the derivative fairly easy. But the derivative of cosine is negative sine. That's not really getting simple. But it is something that's easy to integrate. The antiderivative of cosine is sine. So I really think that I want to let f be x in this case, and dg to be cosine of x dx. And of course, if I want to find out what df is, it's going to be the derivative of x, which is 1. And if I want to find g, I want to take this antiderivative of cosine, which is sine. So I end up with my integral of x times cosine of x dx being equal to f times g minus the integral of g dx. And notice that I went from having a hard integral, one that involved x and a trig function, to an easier integral, one that involves just a trig function and a constant of 1. So this is x times the sine of x. This is going to be the antiderivative of sine, which would be negative cosine x plus a constant. And so I end up with x times the sine of x plus the cosine of x plus c. So this idea of integration by parts takes a hard integral and makes it into something easier. As long as we choose our f and our dg appropriately. Notice again that if I had chosen poorly, if I had chosen to let f be cosine cosine of x, and dg to be x dx, because I have to incorporate all of these parts here. Then df is the derivative is negative sine x dx, and g would be the antiderivative of x, which would be x squared over 2. And my integration of parts of integral x cosine x dx would give me f times g cosine of x times x squared over 2 minus the integral of x squared over 2 times negative sine x dx. Remember that we're trying to make this easier, but this is not at all easier. So appropriate choice of f and dg, and you should be able to tell in this breakdown which one to use, because one of them is going to give you a much more complicated integral to deal with. So in our third example here, I've got the antiderivative of x times e to the x. Remember that we're choosing f so that f simplifies when we take the derivative, and dg should be easy to integrate. And so looking at this, I know that if I take the derivative of x, I'm going to get 1. And if I take the antiderivative of e to the x, I end up with e to the x. I can take antiderivatives all day long with this function. So I'm going to let that be determining my f and my dg. dg is going to be e to the x dx. F is going to be just plain old x. And so df is the derivative, which is 1 dx. G is my antiderivative, which is e to the x. And so the integral of x e to the x dx is equal to f times g minus the integral of g df. And notice I go from an integral that's hard to something that's easier. Because now it's just the antiderivative of e to the x, which is e to the x. So I've got x e to the x minus e to the x plus a constant. So notice that x could be either f or dg depending on the situation. It really depends on whether the other function is either easier to integrate or if it simplifies when I take the derivative. I noticed that with natural log of x. I noticed that with to the x, it's going to be my dg. I notice with the trig function, it's going to be my dg. But I notice that for x, it actually ends up being for x ln x, ln actually ends up being my f, and dg ends up involving x. So we need to go through this idea of separating my f and separating my dg. That's one of the powers of integration by parts, but that's actually the hardest part of integration by parts. There's a couple more examples that I want to talk about today. And in our last lecture, we talked about how we could find the antiderivatives of any of our trig functions. So here I want to talk about how I would find the antiderivative of natural log x. And at first you're looking at this and saying, well, I really only have one function here. And that's not the case. What we actually have here is the integral of natural log x times 1 dx. 1 is a function. It's a constant function. And remember that I need to choose f so that f simplifies, and dg is easy to integrate. So looking at this, I would say let f be natural log of x, and dg be 1 dx. So dg is easy to integrate. The antiderivative of 1 is x. F is easy to take the derivative because the derivative of natural log x is 1 over x. And my integral of natural log of x dx ends up being f times g minus the integral of g df. And notice I go from having a hard integral to an integral that's easier, because this integral is just the integral of 1. So I end up with x times the natural log of x minus x plus a constant. And so this allows me to say that if I wanted to find the antiderivative of just a natural log function, the antiderivative of ln of x dx ends up being x ln x plus minus x plus a constant. And recall that we can always check our answer by taking the derivative of this expression. So if I wanted to take the derivative of x ln x minus x plus a constant, here I'd have to take the product rule. And the product rule says it's going to be the first times the derivative of the second, 1 over x, plus the second times the derivative of the first. That's the derivative of this term. The derivative of this term would just be 1. So I end up with 1 plus the natural log of x minus 1, which is natural log of x, what I started it off with. So the idea here is that I can always check my answer, but being able to separate and determine what is my f and what is my dg is really the key here. If I can identify those, I'm always going to end up with something that's an easier integral, something that I should be able to take very straightforwardly. So I've got one last example I want to do. Let's take the antiderivative of sine inverse x. Remember that when I'm looking at this, I want f to be something that simplifies. And I want dg to be something that's easy to integrate. So looking at this, sine inverse x is not something that I can integrate. As a matter of fact, that's the problem that we're doing. But it does simplify when I take the derivative, because it becomes a rational function. So if I let f be sine inverse of x and dg be my 1 dx like it was in the previous problem, I can take the antiderivative of 1 and end up with x. And I can take the derivative of sine inverse, and I end up with 1 over radical 1 minus x squared dx. And I know you're saying, well, that looks more complicated, but I'm leaving the realm of exclusively pre-calculus, which is where we talked about our trig inverse functions. And I'm going into the realm of algebra 2, where we talked about rational functions and radical functions. So since I'm going back a level in my mathematics class, I really am dealing with something that's easier, something that simplifies. And the integral of sine inverse x dx should be equal to f times g minus the integral of g df. So over here I've got x times sine inverse x minus, over here, this is going to take a little bit more work. But we just finished talking about use substitution. And I've got a composition of functions here. This is really 1 minus x squared to the negative 1/2 power. And so I can let u be 1 minus x squared. And so du is negative 2x dx. Now I've got the x, I've got the dx. I even have the negative part. I just don't have the 2. So negative x dx is really 1/2 du. And so this integral really becomes plus the integral of 1/2 u to the negative 1/2 du. And so now I can use the power rule on this expression. That's going to be 1/2 as a constant coefficient. I've got u to the 1/2, negative 1/2 plus 1 is 1/2, divided by my new exponent, and something happens here. Those cancel. That's beautiful. So I end up with x sine x plus u to the 1/2 power. Well, u is 1 minus x squared plus a constant. So I can use all of the tools of our trade. I can use just finding standard antiderivatives that we've memorized. I can use the power rule. I can use u substitution. But we've added one more tool to our tool belt. The idea of undoing the product rule through integration by parts. Now I promised that I would talk at the very end about a way that we could easily determine our f and our dg. And our textbook gives us this limit term. And limit helps us determine what f. Our f's tend to be more towards the front of the word, and our dg terms tend to be more towards the back of our term. But this limit, each letter stands for a different type of function. Our logarithmic functions, our inverse trig functions, our polynomial functions, our exponential functions, and our trigonometric functions. So the thing is, looking at what I have inside of a function, if I can identify it into two distinct categories, the one that's more to the left are the ones that I'm going to want to use for f, and the one that's more to the right are the ones that I'm going to want to use for dg. And notice x, the only variable that's actually behaved as both, is smack in the middle, because it's easy to integrate a polynomial. It's easy to take a derivative of a polynomial. So it could fall in either directions. Some of these terms are very difficult to integrate. And some of these terms, when I take derivatives, they tend to get more complicated. So that's the reasoning behind this. And we've seen several examples. We've seen an example of each of these types of functions being involved. Tomorrow we're going to continue talking about integration by parts. We'll talk about some situations where sometimes integration by parts has to be repeated. Because remember, this integral that we get is going to be easier. But nobody said it was going to be easy. Sometimes we'll have to take it one more step. But that's another day. This is Mr. Potter. Thank you for watching. Have a great